If you push a child on a playground swing and then watch the brass pendulum of a grandfather clock, you are looking at the exact same physical phenomenon. Both move back and forth, and both do it with a rhythm that is so perfectly predictable you can literally set a watch to it. But why? To figure that out, let's strip the clock and the playground away and look at the bare mechanics. A pendulum consists of just three simple things: a fixed pivot point at the top, a string or rod, and a weight hanging at the bottom, known as the bob. When the pendulum is hanging straight down, it is at rest. Gravity is pulling the bob directly toward the center of the Earth. We call this lowest resting point the mean position. But if you pull the bob to the side and let go, gravity accelerates it back toward the bottom. By the time it reaches that mean position, it is moving entirely too fast to stop. Its momentum carries it up the opposite side, until gravity eventually slows it to a halt at its highest points. These are known as the extreme positions. Gravity pulls it down, momentum carries it up, and gravity pulls it down again. This constant physical tug-of-war traps the bob in an endlessly repeating cycle that creates a steady, measurable rhythm. To measure rhythm, we track specific variables. Amplitude is the angle the bob travels from its resting point. Time period is the exact duration of one full back-and-forth journey. Finally, frequency counts how many complete swings happen per second. Pendulums are counterintuitive. A lightweight bob and a massive anvil will swing in perfect synchronization. Mass has zero effect. Pull one pendulum 5 degrees and another 10, and they cross the center simultaneously. The wider swing travels faster, perfectly compensating for the extra distance. Think about what that means. You can make the weight heavier or swing it twice as hard, and the rhythm refuses to change. Because a pendulum's rhythm is immune to the weight of the object or how hard it is pushed, it serves as an incorruptible timekeeper. When weight and swing width are removed from the equation, only two variables remain to control the rhythm: gravity and the length of the string. Extend the string, and the pendulum takes a longer path, creating a longer time period. The formula T equals 2 pi times the square root of length divided by gravity maps this curve. Exactly a 1 meter string takes 2 seconds to complete one full swing. There is a catch. The perfect predictability only holds up if the swings are relatively small. If you pull the pendulum back to an extreme angle, like 90 degrees, the physics get messy. The motion becomes chaotic, falling out of its predictable rhythm. While air friction will slowly drain the pendulum's energy over time, making each swing a little bit shorter than the last, that only shrinks the amplitude. The underlying time period stays the same until the bob finally comes to a halt. This mathematical relationship functions as a predictable law of physics. It provided the exact blueprint needed to engineer clocks that finally moved past the limitations of the sun or water flow. In the late 1500s, a young Galileo Galilei was sitting inside the grand, towering arches of the Cathedral of Pisa. Looking up, he noticed a heavy metal chandelier swinging gently back and forth in the drafts of the cathedral. Using his own pulse as a makeshift stopwatch, he timed the swings. He realized that even as the swings got smaller and shorter, the time it took to complete each one remained identical. Decades later, Christian Huygens took Galileo's observation and engineered it into a tool. By attaching a swinging pendulum to a set of gears, Huygens invented the world's first pendulum clock. Before this mechanism clicked into place, humanity had no reliable way to track seconds or minutes. Water clocks would freeze, and sundials were useless at night or under clouds. The pendulum gave us our first accurate mechanical heartbeat. By observing a weight hanging from a string and trusting the simple rules of periodic motion, humanity managed to harness the rhythm of nature. We captured the mechanics of a playground swing and used it to synchronize the modern world.